Okay guys, it's Mr. Y. Today we're going to be talking about water's chemistry and the pH scale, and the main goal is to get you to understand why water's unique chemistry is so important for all of life on Earth. So, background that you should have had already in physical science back in 8th grade is this idea that the smallest particle of any material that still behaves the way we expect it to behave is what's known as the atom up here. So, for example, an atom of iron can still conduct electricity, heat, and be attracted to magnets. Anything smaller than that, and we lose those properties. But you can go smaller than that with what we call the 3 subatomic particles. Protons being one you should have definitely remembered because those are the easiest. Those are a positively charged subatomic particle found primarily in the nucleus of atoms. You can see them in 3 different symbolic forms many times. This circle with a plus, this circle with a P, or sometimes even, as you'll see this year, this circle with this H plus, and we'll talk about what that means later on in the lecture. There's also electrons, which are negatively charged subatomic particles found around the nucleus. So they're not in the nucleus space itself of atoms. And again, they come represented by symbolic forms here. This negative charge, this E with a negative charge inside of a circle, or sometimes just the E with a little negative charge by itself. Then there's also the neutrons. The neutrons are neutral. I see students all the time confuse neutrons and think negative. Just think neutrons, neutral. Electrons are negative. These are also, like the protons, found inside the nucleus, and they come with symbolic representations, circle with an end or an equal sign, or sometimes they'll just leave it blank, but there's no charge on any of this, so no charge for these guys at all, whereas these guys are minus and these guys are plus. One key thing to remember with all of chemistry is the idea that opposite charges will be attracted to one another and like charges will be repellent to one another. So a proton and an electron will be drawn towards each other as much as possible, but 2 separate electrons, because they're both negative over here, will be repelled from one another. Likewise, if you had 2 protons without being within the same atom, they would likewise be wanting to get away from each other if they could. So the atom model you are expected to know that you were hopefully taught in physical science is one where the nucleus is composed of protons and neutrons, so the positive and the neutral charges. And around the nucleus is where we find the electrons and what we call electron shells. So this picture, which is I believe similar to one found on page 143 in your text, shows this basic representation, but you can see the electrons are not all equidistant. There's a pair here that are actually closer. This is what's called an electron shell. This is the innermost shell in this case. And then there's another layer here, which is the second shell where the electrons are. And electrons are really small even compared to the nucleus, compared to the protons and the neutrons. Besides being really small, they're also really fast. So this is an inappropriate picture in terms of its size. The electrons would be super small to the point where the best representation I could show you of an atom is actually this picture here. And you can't even see the nucleus because it's so small, it's right in the center. But you can see these 2 kind of dotted layers, and that's these 2 shells. Again, and the dots you're seeing are not electrons. The dots you're seeing are actually the probability of finding electrons in those areas, because again, they're small and they move very, very fast. So fast it's impossible to actually see them. Now, the way that atoms work primarily is by sharing electrons to make bonds. The 2 major types of bonds you're going to need to understand water's unique properties are what are called covalent bonds to start off with, and hydrogen bonds coming on the next slide. But I'm going to talk about covalent bonds because this is where atoms will typically share electrons. So there is sharing of electrons to make these bonds, but with covalent bonds, there's sometimes atoms that are not always equal in their sharing, and I'll explain what I mean. So a regular plain old covalent bond is sometimes also referred to as a nonpolar covalent bond. So this is what you would consider as regular or normal for the covalent bond side of things. And methane gas is a good example, but we have to talk about water, which kind of has this alternative way of doing this sharing of electrons. With methane gas, these lines represent the sharing of a pair of electrons in each case. So there's a pair being shared between the carbon and each of these hydrogens. So a pair here as well. This is just the same exact model. It's just one's in a 3D form and one's in a 2D form. So this straight line there represents a plain old nonpolar covalent bond where the electrons between the carbon in the center and each of the hydrogens is being shared roughly equally. Water doesn't take this approach. Water doesn't share the electrons equally. It does share the electrons, but, and actually let me revise that a bit, the electrons are actually a bit closer to the oxygen side of the end of the sharing. Hydrogen is still being allowed to share with the electrons, but oxygen is kind of in a tug-of-war situation, pulling the electrons closer to itself. And as a result, we get these slight charges on a water molecule. That's what this little symbol means. It means slightly. So the hydrogens end up being slightly positive because they have most of their charge being drawn from their own nucleus, where the oxygen ends up being slightly negative here because it has the electrons closer to itself. And the way we know if a compound will be polar covalently bonded, that's say if it's going to have these slight charges like water actually does, is if there's a large difference in what we call electronegativity. Don't let this word scare you. Electronegativity is actually really just a kind of a measure of strength. It's how strong an individual atom can pull electrons towards itself. There's a scale for it. It runs 0 to 4. And if you look at the periodic table, typically the weakest atoms that hold on to electrons are on the left side and the strongest ones are on the right. The two extremes, francium, which is I believe over here somewhere on the left, is rated at 0.7 and basically just gives away its electrons, but it still shares them, so it lets the electrons be unequally shared very easily, whereas fluorine is very good at pulling on electrons towards its nucleus. And again, when I say the word nucleus, please don't confuse nucleus of an atom with the nucleus of a cell. Those are not the same thing. So back with methane gas, the electronegativity rating for hydrogen is 2.2. For carbon, it's 2.5. And so there's a very little difference. There's only a 0.3 difference here. Again, we know a compound will be polarly covalent bonded if there's a large difference. And again, the scale runs 0 to 4. So 0.03, not that big of a difference. Whereas with water, again, hydrogen is 2.2 on the scale for electronegativity. Oxygen is 3.4, and so our difference here is now 1.2. And again, the scale only runs 0 to 4. And on a 0 to 4 scale, a difference of 1.2 is a rather large difference. So oxygen is pulling on the electrons harder than hydrogen is. Hydrogen is still being allowed to share them, but the electrons are being pulled a little bit further on this end. So again, you can kind of think of it like a weird case of tug-of-war where nobody wants to let go. So hydrogen bonds in water end up coming about because water is what we call polar covalently bonded. So water has these, again, these slight charges, these slight negatives and these slight positives, and because of that, water molecules can form other types of bonds with other water molecules. So the way we represent that is not by the solid line, which you saw me use for covalent bonds or polar covalent bonds, but a hydrogen bond is represented by a dotted line. And of course, in reference to the name, you can't have a hydrogen bond without hydrogen in each of these scenarios. So hydrogen has to be there. It doesn't have to be on both sides, but it has to be there every time. Get rid of this so we can work a little bit more. And usually what happens is hydrogen ends up being the slightly positive end, and then some other atom on some other molecule, for whatever reason, is in a polar covalent bond itself with its own molecule and ends up being slightly negative, and again, opposite charges tend to attract. So those solid lines, again, are the polar covalent bonds. Those dotted lines are the hydrogen bonds. So hydrogen bonds get a dotted line, covalent bonds get a solid line. If it's polar covalent, you'll also see that little charge system show up. Hydrogen bonds are really weak compared to covalent bonds. They're about 1/20th the strength. And so covalent bonds were what you typically see in chemicals, hydrogen bonds, while they are weak on their own, they can often form very quickly and in very huge numbers. So for example, DNA. In DNA, the entire center, get this pen to work here, yeah, the entire center of the DNA here is held together with nothing but hydrogen bonds. Hydrogen bonds also explain why you can have this weird property. If you think about it, a solid of a basic compound should be denser than the liquid form. So if you had like a solid piece of gold, you would expect it to sink in liquid gold if you put the two together. But with ice, with water, the solid actually floats in the liquid. And that is a very weird property, liquid. And part of the reason for that is because water has this capacity to form hydrogen bonds with other water molecules. So here we see, again, here's one water molecule, here's another. They kind of look like, Mickey Mouse. And you can see the dotted line between them. And why is that there? Because there's a slightly negative charge on this oxygen, and there's a slightly positive charge on this hydrogen. And so they're somewhat attracted to each other. But again, this bond is relatively weak. If you're talking about liquid water, that can break pretty easily. And when you look at this overall, you can see one single water molecule here in the center has the ability to actually form 1, 2, 3, 4 hydrogen bonds with 4 other water molecules, because you have slightly negative charges, and put this in red, slightly negative charges here and slightly positive charges here on just the center guy, and then again, the hydrogen bonds will make it attached to other water molecules. This kind of makes water have some weird properties. Any of you who've watched water going down a window on a rainy day know that water tends to stick together. Well, it's hydrogen bonds that cause this, so the water pathways will tend to all converge into one main path once it's formed, and it will speed up. A droplet would speed up once it hits that main pathway. You can see this even here on the leaves where the water kind of condenses in a weird way. This is also partially why when you put water in a very small container, you get this meniscus effect. Let me use yellow for that. This meniscus effect right here, where water actually sticks to the side and the molecules up here are actually pulling the water upwards towards each of the sides, and yet there's nothing in the center, so the center tends to sink down a bit. So again, DNA has nothing but hydrogen bonds running throughout this entire strand. All of your DNA is held together with nothing but hydrogen bonds. They are weak, and you can barely make it out, but there's actually a dotted line there. But they come in such massive numbers often enough that that makes up for any apparent weakness in comparison to, say, these polar covalent bonds that you would see like here and here, or regular covalent bonds too. So those all get solid lines. Hydrogen bonds get these dotted lines. So literally all the DNA in every organism is held together with a hydrogen bond. When water forms these hydrogen bonds, again, in liquid, these things can break apart very easily because water is very fluid, it has a lot of space to it. But when you drop the temperature in water, these charges, again, will form hydrogen bonds, but they become slower. The molecules slow down. That's what happens when you lose heat. And as a result, you get this weird lattice structure. And you can see this lattice structure, just blue, has space in it. And that's where air can get in. And when that air gets in, it makes the solid, ice, less dense than the liquid. Hence, ice, up here, can actually float in liquid water, even though it's the solid version. Again, that's a very weird property. And it's thanks to this lattice structure, and the reason we have air stuck in this lattice structure is because these hydrogen bonds make this pretty little uniform bonding system between water molecules and their neighboring water molecules. So again, the basics for water, make sure you understand at the very least, water is consisting of 2 hydrogen atoms and 1 oxygen atom, H2O. And again, if you talk about just the electrons are being shared, so the hydrogens and the oxygen are sharing electrons, and most of the times we just represent that with a single line here showing this polar covalent bonds. And again, in reality, it should have these charges on it, like we see here. And if you actually look at the true nature, this is a good picture. It just doesn't show the neutrons. Hydrogen doesn't have neutrons, but oxygen does. You can see the electrons here and here are being pulled slightly closer to the nucleus. Thus, the oxygen ends up being slightly negative. The hydrogen side ends up being slightly positive. The reason I'm teaching you all this is because that most of the biological reactions that occur in cells, i.e. in your body, occur in water. Because water is the prime medium by which most reactions occur. It doesn't really happen in air. Your body is not composed mostly of air. It's composed of water. So understanding how water behaves makes understanding certain chemical processes easier. For instance, water itself can naturally break itself down on occasion. And what I mean by that is if these were the outer shell electrons in a water molecule, on occasion this water molecule can split apart. You'll notice this is a double-ended reaction, meaning if you have two of these end products, it can in fact go backwards, but it can also go that way. When it breaks itself apart, because water has three atoms, it doesn't break apart evenly. You can get what we call a hydrogen ion or a hydroxide ion. And you notice these things have charges to it. There's a +1 and a -1. These are not slight charges like we see up here, but these are full-blown true charges. And try not to confuse a hydrogen ion and a hydroxide ion. They're not the same thing. So when we look at these, what we see is the hydrogen ion is actually a hydrogen atom with no electrons whatsoever. And because hydrogen never had any neutrons to begin with, it's the smallest element on the periodic table, a hydrogen ion is literally just a proton. Hence, this symbol came up when I first discussed protons. A hydroxide ion is a combination of the remaining hydrogen ion from the initial water molecule and the oxygen. They are still polarly covalently bonded, but the oxygen now has an extra pair of electrons. Where did it get those electrons? From this hydrogen ion back over here where it was bonded to as a water molecule. And so this gives us our definitions for the terms acid and base, whereas an acid is any compound that when dissolves in water increases the concentration, that's what these brackets mean, the concentration of hydrogen ions. Whereas in a base, I'll do this in red, a base is any compound that when dissolved in water increases the concentration, again that's what these brackets mean here in the black, of hydroxide ions. So there's this counterpoint to each other, and it's all based upon water. So just remember the brackets mean concentration of whatever's inside the brackets. So in this first one it's concentration of hydrogen ions, and the second one it's concentration of hydroxide ions. We measure the strength of acids or bases by what we call the pH scale. And the way it works is the pH scale runs 0 to 14. And so here's an example. If you go 0 to 14, your naturally middle area is 7, and that is where the amount of hydrogen plus is equal, that's a plus, to the amount of hydroxide. And hence we define 7 as being where you find pure water, where these two are equal. When you have more of the hydrogen ions, that means you're going down on the scale. So your pH number gets less. When you're going with more hydroxide ions, you're going up on the scale, so the pH number gets higher. And these are all common examples on these two. If you want to pause the video and take a look at a few of these to understand a few that you're familiar with, it should make sense with what your experience is. Here's another example. I like this example a bit better, so if you're going to get one for your notes, I would get this one and make sure you include these little circles here, because what it shows you is at 7, pure water, the hydroxide and the hydrogen ions are more or less equal. That's pure water. Whereas up here, again, notice the numbers are going down, because here's 0. We have more hydrogens than hydroxides, and again, you can see that over here. There's a lot more hydrogen ions in this little circle than there are hydroxide. And then on the opposite end, when you go the other direction, you have more hydroxide than hydrogen. So this is getting more and more basic, which you can see right here. That's the basic understanding of the pH scale that they may have introduced to you, hopefully in 8th grade, but I want to take this one step further if we can. The power of the pH scale is that it's actually what we call a logarithmic scale, and I don't necessarily expect you to understand the mathematics behind it just yet, but basically what that means is that the scale is not equally spaced like you'd normally expect. For instance, you might be thinking in your mind that each pH number is more or less you could say equidistant if you're thinking about a ladder, from one another. So the difference between here and here, pH 1 and 2, is the same as the difference between pH 2 and 3, which is the same as pH 4 and 5. Unfortunately, that equal spacing idea is completely and totally wrong. The pH scale works differently. It works by what we call a logarithmic system, where if this is the difference in space between pH, say, 6 and 5, we're going to get more acidic as we go here. The difference between 5 and 4 is about 10 times more that. So going from 6 to 5 is an increase by a factor of 10, and then going from 5 to 4 is another increase in a factor of 10. And then going from, say, 4 to 3, and if you combine the two, going from 6 directly to 4, so from here directly to here, you're increasing by more than a factor of 100. Sorry about that. If you go from a pH of 4 now to 3, this is not realistic. In reality-wise, it should be this space, again, times 10. Times 10. There we go. So, again, another 10 times more acidic, meaning to go from a pH of 6 to just a pH of 3, you are increasing by a factor of 1,000 in terms of how strong your acid is. Again, this whole equal spacing idea doesn't work. So 6 to 5 gets 10 times more acidic. 5 to 4 gets 10 times more acidic. 4 to 3 gets 10 times more acidic. But if you jump numbers, if you go from 6 straight to, again, 4, that's 100 times more acidic. If you go from 6 straight to 3, that's 1,000 times more acidic. And the same thing is true going in reverse above 7. So if I went from 8 to 9, that's 10 times more basic. If I went from 8 to 10, that's 100 times more basic. If I went from 8 to 11, that's 1,000 times more basic. So it works the same way, and so it's really hard to kind of impress upon you how big this scale actually takes things into account. So the pH scale, again, runs 0 to 14. There's actually an alternative scale known as the POH scale that runs exactly in the opposite direction. They may expose that to you in chemistry, but don't worry about it for biology just yet. But just focus on the idea that the pH scale has this center area, and again, every time you go up or down, it increases things by a factor in terms of strength of either acids or bases of 10 for each integer. So what you should be able to do is take a look at any of these pH numbers that I'm providing here on the screen and be able to tell me, is it an acid, is it a base, and is there a higher concentration of hydrogen or hydroxide ions? So I'm going to do one for you. Let's just do this one over here, pH of 2.6. 2.6 is less than 7. So it's less than 7 on the scale, which makes this an acid. And because it's an acid, by definition, it has to have a higher concentration of hydrogen ions compared to the concentration of hydroxide ions. And again, most of these will be liquids. Not always, but mostly. And again, you should be able to do the same basic format for any of these. So go ahead and pause the video and try it on your notes, see what you can do, and then I'll run through real quick and make sure you have what you have. So pause it if you wish right now. Okay, running through real quick, pH 5.6, that is an acid. And again, the hydrogens are greater than the hydroxides, OH minus. Make sure you remember the charge symbols. pH 12.8, that is a base. And so the hydrogens are now less than the hydroxides. 10.1, that is a base as well, because it's above 7. So the hydrogens and the hydroxides are definitely not equal, just to be clear. And you want more hydroxides than hydrogens. 8.8, it's close to 7, but it's not 7. So again, the hydrogens, hydroxides are definitely not equal, and even here, just because it's close to 7 doesn't make it 7, so you still have a base where you have more hydroxide than hydrogen. Now here, this is neither an acid nor base. This is simply what we call neutral. In other words, pure water. Just because it's neutral doesn't make it pure water, but it's the same as what we would refer to for pure water. So pure water is always considered neutral. And so for here, the hydrogens and hydroxide would be equal to one another. Okay, so I hope that helped. Make sure you let me know if you have any questions in class.